Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today, we are exploring supramolecular chemistry. And to start us off, I really want to kind of set the stage for what we are actually looking at today. Because the material we are going over is, well, it completely shifts how we view the physical world.
It really does. It is a real pleasure to be here, by the way. But yeah, usually when we talk about science or chemistry, we are talking about the components, the nuts and bolts of a system.
Right.
But today is different. Today is all about the space between those nuts and bolts.
Exactly. And if you are anything like me, when you think about chemistry, at least the chemistry we all learned in high school, you immediately think about the molecule. You think about the brick.
Yeah, the solid building block.
Right. We learned that atoms lock together in these very rigid structures. You draw the little straight lines between the carbon and the hydrogen and the oxygen on the chalkboard. And that is kind of the end of the story.
That is the classical view, sure.
But based on our sources today, we are not talking about the brick. We are talking about the mortar. We are talking about the invisible forces that happen between the molecules.
That is a perfect way to frame it, actually. Because for a really long time, centuries, honestly, chemistry was entirely obsessed with the individual brick.
Making the brick.
Right, making it. We spent all our time and energy figuring out how to weld atoms together to make one specific molecule. But supramolecular chemistry is literally defined as the science of chemistry beyond the molecule.
Chemistry beyond the molecule.
Exactly. It is not about how atoms bond to form a structure. It is about how those structures recognize each other out in the wild, how they shake hands, and how they build massive, incredibly complex systems entirely without human intervention.
And just to hook everyone right from the start, so you know why you should care about this.
Yeah.
We're not just talking about abstract academic theory here.
No, not at all.
This isn't just stuff happening in a dusty beaker in a basement that nobody cares about. This is the exact science that explains how your DNA holds itself together without just falling apart into mush.
Yeah, it is the foundation of biology.
It explains how your body heals a wound. And as we are going to find out a bit later, it is how scientists are currently building actual functioning motors that are 1,000 times smaller than a single human hair.
It is the chemistry of life. And it is definitely the chemistry of the future.
So let's unpack this. We need to start with the absolute foundations, the things we think we know.
Always a good place to start.
Right. So if we are talking about chemistry beyond the molecule, we have to define what the traditional molecule actually relies on first. I have this image in my head of molecules being these permanent, indestructible things.
Right. Well, the traditional view of chemistry is built entirely on the covalent bond.
The covalent bond.
Yeah. These are very strong, very permanent relationships where atoms literally share electrons. Think of this like welding or maybe gluing two pieces of metal together.
Okay, so it's a structural commitment.
A huge commitment. Once you weld two pieces of metal together, they are effectively one single piece of metal. It is very hard to break that connection without completely destroying the materials involved.
Okay, so the covalent bond is the weld. It is the permanent commitment. It's like a marriage.
In a way, yeah, a very traditional marriage. But the supramolecular view focuses on non-covalent interactions.
Non-covalent, so not welded.
Exactly. If a covalent bond is a marriage, like a legally binding till death do us part kind of situation, supramolecular interactions are much more like a handshake.
A handshake.
Or a hug, or maybe even a dance partner.
Oh, I kind of like the dance partner analogy.
Mm-hmm.
Because you can change partners. You can step away, but while you are holding hands, there's a real physical connection.
Right. It is dynamic. It can change.
But here is where I get stuck looking at the research. If these forces are weaker, if they're just a casual handshake, how do they build anything remotely stable? I mean, I am made of supramolecular chemistry, right?
You are. Your cells, your proteins, everything.
Right. And I do not feel like I am falling apart into a puddle. I feel pretty solid.
And that is the absolute magic of it. It is all about strength in numbers.
Then numbers.
Yeah. One single handshake is extremely weak. You can break it easily. But imagine a million handshakes happening all at the exact same time.
Okay, that would be harder to break.
Right. That is incredibly strong. Imagine trying to pull two phone books apart. If you have interleaved every single page.
Oh, I have seen videos of that. You can hang a car from them.
Exactly. The friction on one single page is nothing. You barely feel it. But the friction on 1,000 pages combined makes it literally impossible to separate them.
So it's a cumulative effect.
Completely. We usually talk about the big four interactions when we discuss the sort of molecular Velcro effect.
Let's run through those. The big four, from the sources. What is number one?
First up, you have electrostatics.
Electrostatics.
Yeah, this is basically an ionic interaction. Positive attracts negative. It is actually quite a strong force on its own. Think of basic table salt. Sodium chloride.
Right, the white crystals on your kitchen table.
Exactly. The sodium is positively charged and the chloride is negatively charged. They stick together very, very tightly in that crystal formation.
But wait, if I throw a pinch of salt into a pot of water, it just dissolves immediately. It vanishes. So it can't be that strong of a bond.
And that is the exact catch. Electrostatic interactions can be incredibly strong when they are in a vacuum or in a dry, solid state, but they are very vulnerable to their environment.
Because of the water.
Right. The water molecules rush in and completely surround the ions. They pull them apart because the water is basically competing for that electrical attention.
Oh, so the water plays home record to the salt.
Exactly. So electrostatics are strong but highly context dependent.
Okay, context matters. So what is number two on the list?
Number two is hydrogen bonding, and this is honestly the glue of life.
The glue of life. That sounds important.
It is arguably the most important one for us. It is a specific type of attraction between a hydrogen atom and something that is highly electronegative, usually oxygen or nitrogen.
Electronegative meaning it really wants electrons.
Right, it pulls electrons towards itself, so it creates this strong partial charge. It is not a full covalent bond, but it is a very, very strong suggestion of one.
And this is exactly why water is a liquid, right?
Yes, perfectly stated. Think about it this way. Methane is a molecule of very similar size and weight to water.
Methane, like the gas.
Right. It is a gas at room temperature. It just floats away into the atmosphere. But water stays liquid. And the only reason it stays liquid is because the water molecules are constantly holding hands with each other via these hydrogen bonds.
So they form a sort of invisible network.
A massive shifting network, yeah.
Yeah.
And it is also the exact same reason why your DNA stays zipped up.
Oh, the double helix.
Right, the two long strands of the double helix are not welded together covalently. They are held together by millions of these tiny hydrogen bonds right down the middle.
Which is super crucial because DNA has to unzip to be read by the cell, right?
It is the only way life works. If DNA were covalently bonded, if it were actually welded shut, your cells could never read the genetic code to make proteins.
And you'd just be dead.
You would never have existed. Life depends entirely on that reversibility. It needs to zip and unzip constantly, day in and day out.
Wow. Okay. So moving down the list, we have electrostatics, we have hydrogen bonds. What is the third force?
The third is van der Waals forces, and these are the absolute weakest of the bunch.
The weakest.
By far. They arise from very temporary fluctuations in electron clouds.
Okay, temporary fluctuations in electron clouds.
Yeah.
That sounds a bit like Star Trek technobabble.
Yeah.
What does that actually mean for the rest of us?
Fair enough. Okay, imagine the electrons whizzing around an atom like a crazy swarm of bees around a hive.
Okay, a swarm of bees.
On average, if you look at them over time, they're spread out pretty evenly around the hive. But for a split second, purely by random chance, the entire swarm might suddenly shift to the left side.
Just randomly all on one side.
Right. And that creates a tiny temporary negative electrical charge on the left side of the atom and a tiny positive charge on the right side.
Because all the negative bees went left.
Exactly. And that tiny temporary charge induces a reaction in the neighboring atom. It basically says, hey, I am negative over here, so you need to be positive over there.
And opposites attract.
Right, and they pull together. But just for a fraction of a second.
It sounds incredibly fleeting. Like it shouldn't actually matter at all in the real world.
It is wildly fleeting. It appears and disappears constantly millions of times a second. But again, you have to multiply it by billions and billions of atoms.
Strength in numbers again.
Always. And this is actually how geckos stick to walls.
The geckos. Like the little lizards.
Yeah, the lizards you see climbing straight up a glass window. They do not have glue on their feet. And they don't have little suction cups either.
I totally thought they had suction cups.
Most people do. But they actually have millions of these incredibly tiny microscopic hairs on their toes called setae.
Setae, okay.
And those hairs branch out into even smaller microscopic spatulae. So what they're doing is creating a massive amount of physical surface area that is incredibly close to the wall.
Oh, I see. So because there is so much surface area, all those billions of tiny, weak van der Waals fluctuations add up.
Exactly. They add up enough to hold the entire body weight of the lizard against the force of gravity.
That is wild. Just pure geometry and quantum fluctuations holding a lizard on a ceiling.
Nature is pretty clever.
Okay, so what is the fourth and final force?
The fourth one is called pi effects. This involves interactions between aromatic rings.
Aromatic rings like benzene.
Right, molecules shaped like a hexagon. These rings have these sort of clouds of delocalized electrons floating just above and below the flat ring.
Like a molecular hamburger bun.
That is a great visual, and those electron clouds can interact with each other. They can essentially stack on top of each other like dinner plates in a cafeteria.
And I read that this is the structural support for DNA, too.
It is a massive part of it, yeah. The rungs of the DNA ladder, the letters of your genetic code, are actually these aromatic bases stacking directly on top of each other.
So they stack up like coins.
Exactly. It provides the crucial vertical stability to the entire helix. So while the hydrogen bonds we talked about hold the two strands together side by side, the pi stacking gives the whole thing structural integrity from top to bottom.
Okay, so we have these four foundational forces. We have the electrostatic static cling, we have the hydrogen bond hug, the van der Waals swarm of bees, and the pi effect stack of plates.
Good summary, yeah.
But here is the thing. How do we use these to actually do something? Because random hugging and stacking doesn't build a functioning machine.
Yeah.
I can go out and hug 100 people in a crowded room right now, but I haven't built a car.
No, you just have a very awkward room.
Right. So how does nature build things with this?
That brings us to the core concept of molecular recognition. This is really the beating heart of supramolecular chemistry.
Molecular recognition.
Right, because it is not enough for molecules to just stick together randomly. They have to stick to the exact right thing at the exact right time. We call this host-guest chemistry in the field.
The host and the guest. It sounds very polite.
It is remarkably civilized for chemistry. Basically, you have a large molecule, which is the host, and it has a cavity, or a very specific three-dimensional shape, designed to perfectly accept a smaller molecule, which is the guest.
Like a molecular hotel?
Kind of, yeah. And this whole field really exploded into the mainstream with the Nobel Prize in Chemistry back in 1987.
Yeah, I have notes on this. It was awarded to Donald Cram, Jean-Marie Lannes, and Charles Peterson.
The pioneers of the field. And Peterson's story is particularly fascinating. He wasn't even a traditional academic working at a university.
Right, he was an industrial chemist working at DuPont.
Yes. And the story goes that he discovered these things called crown ethers, essentially by total accident.
A happy accident.
Very much so. He was trying to synthesize something completely different, and he ended up with this weird little bit of undefined goo at the bottom of his flask.
Which usually means you failed.
Usually, yes, you throw it out. But he analyzed it. And he realized he had accidentally created these ring-shaped molecules that contained oxygen atoms.
Okay, so a ring of oxygen.
And he found that these rings acted exactly like a physical crown that could sit perfectly on top of a specific metal ion, like a potassium ion.
Just sitting right on top of it.
But here's the key. The size of the ring had to match the exact size of the ion.
Oh, like trying on hats.
Precisely. If the crown is too big, the potassium ion just falls right through the middle. If the crown is too small, the ion simply won't fit inside.
So it's a physical sorting mechanism.
Exactly. This was the very first clear demonstration of synthetic molecular recognition. We proved that we could design a molecule in a lab to grab only potassium and completely ignore sodium based entirely on its physical size.
This sounds a whole lot like the lock and key principle we always hear about in basic biology.
It is the exact same principle.
Yeah.
Emil Fischer originally proposed the lock and key concept way back in 1894 to explain how enzymes work.
He said the enzyme is the lock and the substrate is the key.
Right, and they have to fit together perfectly for a reaction to happen. But the 1987 laureates took that biological concept and proved we could replicate it with synthetic chemistry in a glass beaker.
So we didn't need millions of years of evolution to do it for us. We could just engineer it from scratch.
We could build our own locks and keys.
There is a term that kept popping up in the literature regarding this pre-organization. It sounds a bit like corporate middle management speak, to be honest. But I suspect it means something very specific chemically.
It is a vital concept. Think of it this way. Imagine you have a very chaotic, messy living room.
Okay, easily done.
And you want to invite a very important guest inside to sit down. If you have to clean the room and arrange the furniture and fluff the pillows after the guest arrives, it takes a huge amount of energy and effort.
Yeah, you are sweating, and the guest is just standing there waiting while you shove a sofa across the room.
Right, it's high energy and very inefficient. But if the room is pre-organized, if the armchair is already facing the right way, the clutter is put away, the lighting is perfect, the guest can walk in and sit down immediately and comfortably.
No energy wasted.
Exactly. So the host molecule needs to be built in a rigid, predefined shape that is already perfect for the guest. It doesn't have to awkwardly bend or warp itself to make the guest fit.
It is pre-organized.
Yes. Preorganization vastly lowers the energy cost of binding, and because it lowers the energy cost, it leads to much higher selectivity.
Selectivity meaning the ability to pick one specific molecule out of a soup of millions of other molecules.
And that is the holy grail of chemistry. That is exactly how your immune system works right now.
Oh, right, finding the virus.
It recognizes a specific virus protein that is distinct from your own healthy cells. If we can master that kind of selectivity in the lab, the applications are endless.
Like what kind of applications?
We could build chemical sensors that detect a single microscopic molecule of a deadly toxin in an entire swimming pool of water. Or we could design smart drugs that only target and bind to cancer cells while completely ignoring the healthy tissue.
It really is amazing to think that all of this is happening just based on three-dimensional shape and those weak little forces we talked about earlier. No heavy welding involved.
Just geometry and a chemical handshake.
But that brings up a huge question for me. If we are not welding things together, how in the world do we build large structures? How do we go from a simple handshake to a skyscraper?
That leads us perfectly into the next massive concept in the field, self-assembly.
Self-assembly, nature's ultimate blueprint.
Yes. Andrew, I want you to imagine you have a large cardboard box full of car parts.
Good car parts. Pistons, gears, tires.
The steering wheel,
No.
the chassis, everything. You throw every single piece into this giant box, you tape it shut, and you shake it up violently for an hour.
Okay.
And when you finally open the lid, what do you see inside?
Well, I just have a very heavy pile of broken metal. And I probably made a ton of noise doing it.
In our normal macroscopic everyday world, yes, that is exactly what happens. But in the world of supramolecular chemistry, if you design the chemical parts correctly, you open the box and you pull out a fully assembled running Ferrari.
Okay, hold on. I get the analogy, but that just sounds like actual magic. I mean, the basic laws of entropy say that things should naturally get messier and more disorganized over time, not cleaner and more complex. How on earth do we get a Ferrari out of total chaos?
It does sound counterintuitive, it sounds like magic, but it is just fundamental thermodynamics.
How so?
This system as a whole naturally seeks out the lowest possible energy state. It wants to relax.
Okay.
If the fully assembled Ferrari state is energetically more stable and relaxed than the chaotic pile of parts state, and if the parts have enough thermal energy to constantly move around and bump into each other, they will inevitably find each other and click together.
Because the connections are reversible, right?
That reversibility is the secret ingredient.
So if a tire accidentally attaches to the windshield.
Which is energetically wrong and structurally awkward.
Right. It just falls off because the fit isn't quite perfect.
Exactly. It pops off and it keeps floating around trying different connections until it finally finds the axle. And when it hits the axle, it clicks into a deep, stable energy well and it stays there.
So it's basically a self-correcting puzzle.
We literally call it error correction. Reversibility allows the entire system to continuously correct its own mistakes until it finds the absolute thermodynamic minimum, which is the perfect, fully assembled structure.
We see this happening in biology all the time, don't we?
Constantly. You couldn't exist without it. The tobacco mosaic virus is the classic textbook example of this.
How does that one work?
It is made up of thousands of individual protein subunits and one single long strand of RNA. Scientists can take a functional virus, separate all those parts in a test tube, so it's just a chemical soup.
A disassembled virus.
Right. But if you just mix them back together under the right conditions, they will spontaneously reassemble themselves into a fully functional infectious virus.
With no help?
None. No little biological construction workers needed. The parts just know where to go based on their shape, or look at lipid bilayers.
The cell membranes, right?
Yeah, the barrier of every cell in your body. They form completely spontaneously because the head of the lipid molecule loves water and the tail portion absolutely hates water.
So they just naturally line up to protect the tail.
Exactly. Jean-Marie Len, one of those Nobel winners we mentioned, had a truly great quote about this phenomenon.
Oh, I think I have that in the notes. He said, matter becomes complex under the pressure of information.
It is such a profound insight into how the universe works. He's saying that the complex instructions for building a massive biological structure are already hard-coded into the physical shape and the electronic profile of the individual molecules.
The molecule itself is the blueprint.
Exactly. We talk about the information age, meaning computers and silicon. But Len is pointing out that matter itself stores the exact code for its own physical construction.
Okay, so we have essentially laid the solid foundation here. We have the weak handshake bonds. We have the host gas molecular recognition. We have the self-assembling Ferrari.
The basic toolkit.
But science is never truly settled, is it? We have the theory down, but looking through the provided sources, there seems to be some pretty intense philosophical friction in the field right now.
There is always friction. And in supramolecular chemistry, the arguments get very deep very quickly.
Let's move into that active debate section. Where does the science actually disagree right now? One of the biggest friction points I saw seems to revolve around the very definition of life versus just complex chemistry.
This is where we step into a subfield called systems chemistry.
Systems chemistry.
Yeah, this is the study of vast networks of interacting molecules rather than just one or two in isolation.
Yeah.
And the fundamental debate here is incredibly philosophical. Where exactly is the line?
The line between alive and dead.
Right. If I design a purely chemical system in a lab that actively consumes chemical fuel, replicates itself over and over, and adapts to its environment, is that system alive?
We have a source here from a researcher named Peter Strzeski that touches heavily on this exact question. And he seems to warn chemists about getting carried away with their metaphors.
Yes. Strzeski is very cautious, and rightly so. He brings up a really wonderful reference to the famous surrealist painting by René Magritte.
Oh, the treachery of images painting.
Exactly. It is a painting of a very realistic smoking pipe, and written in French underneath it says, "This is not a pipe."
Because it's not a pipe. It's just a painting of a pipe on a canvas. You cannot pick it up and smoke it.
Exactly. And Strzeski says chemists really need to internalize this lesson. He literally says we cannot smoke with Magritte's pipe.
Meaning what exactly in this context?
Meaning that just because a complex chemical system in a test tube behaves sort of like life, or just because we use biological words like translation or evolution to describe what it's doing, that doesn't mean it is actually alive.
We are just projecting our own biological metaphors onto a chemical reaction.
Right. We have to be very careful not to fool ourselves with our own vocabulary.
But the line really is blurry, isn't it? I mean, think about viruses again.
Viruses are the ultimate gray area in biology.
Because a virus self-assembles perfectly. It has genetic material. It visibly evolves over time to beat our immune systems.
But it has absolutely no internal metabolism. It doesn't eat, it doesn't breathe. Outside of a host cell, a virus is essentially just a highly organized crystal.
So is it alive or is it a machine?
It depends entirely on who you ask. A lot of supramolecular chemists argue that life isn't a magical spark. They argue that life is just a system property that naturally emerges when basic chemistry gets sufficiently complex.
So there isn't a sharp dividing line between dead matter and living matter. It's just a smooth gradient of complexity.
Exactly, it's a spectrum. And that specific debate leads directly into another major hurdle we see in the sources, the distinction between static and dynamic self-assembly.
This seems to be the major roadblock in actually creating any kind of artificial life.
It is arguably the biggest hurdle we face today. Because most of what we have discussed so far, the salt crystal dissolving the virus shell, assembling the self-assembled Ferrari, all of that is what we call static self-assembly.
Meaning once it's built, it's done?
Exactly. You mix the parts together, they find their lowest energy state, they form the structure, and then they just sit there forever. They are at total equilibrium.
They are chemically dead.
Right. They do not do any work once they are built.
But that doesn't sound like me. I am not static. If I just sit on the couch and stop eating and stop breathing, I don't stay in a stable, happy state. I die and decompose.
A bit dark, but perfectly accurate. You are what we call a dissipative structure.
A dissipative structure?
Yes. You require a constant, massive input of outside energy, food, oxygen, sunlight, just to maintain your basic physical organization.
Because if the fuel stops, the organization stops.
Right. You degrade back into simple chemicals. That is dynamic self-assembly. A great way to visualize it is to think of a decorative water fountain.
Okay, a fountain.
The physical shape of the water shooting up in the air looks constant, it looks solid, but it is only maintaining that shape because a pump is constantly forcing new water and new energy through it.
Oh, I see. And the second you pull the plug on the pump, the shape completely collapses into a puddle.
Exactly. So the massive challenge for chemists right now is to figure out how to make synthetic molecules that only assemble themselves while fuel is actively being added and immediately fall apart when the fuel runs out.
And based on the research, that is incredibly difficult to do in a lab.
It is mind-bogglingly difficult because chemistry naturally wants to go to sleep. It wants to go to the lowest energy resting state and stay there.
But life doesn't want to rest.
No, life is a constant, exhausting battle against equilibrium. There is a saying in systems chemistry, equilibrium is death.
Equilibrium is death. That is a really heavy philosophical concept, honestly. It literally implies that total relaxation is the fundamental enemy of existence.
Thermodynamics is a very harsh mistress.
Okay, let's touch on another fascinating debate that came up in the source material. It goes back to something we mentioned briefly earlier, the hydrophobic effect.
Ah, yes, the classic oil and water misconception.
Right, so the common conventional wisdom, the thing we are all taught as kids, is that oil and water actively repel each other. They push each other away. Like water somehow inherently fears oil.
That is exactly how it is usually taught. But chemically speaking, there is actually no repulsive force happening there at all.
Wait, really? None at all.
None. In fact, an oil molecule is actually slightly attracted to a water molecule via those weak van der Waals dispersion forces we talked about.
So they don't hate each other.
No. The real driver behind why they separate is entirely based on entropy.
Entropy again. The universe's desire for disorder.
Always entropy. Here is what is actually happening on a molecular level. Liquid water molecules are highly, highly organized. They form this vast, beautiful, three-dimensional network of hydrogen bonds.
They really love holding hands with each other.
They do. So when you aggressively mix a drop of oil into the middle of that water, it violently disrupts their happy network. The oil molecule can't form hydrogen bonds.
So this is getting in the way.
It is a massive physical roadblock. So the water molecules that are trapped immediately surrounding that drop of oil are forced to freeze into a highly rigid geometric cage just so they can maintain their hydrogen bonds with the other water molecules around the oil.
Oh, wow. So they form a microscopic ice-like shell around the oil droplet.
Exactly.
But wait, so the water loses its freedom to move around? It becomes highly ordered. And we know nature absolutely hates order.
Nature strongly prefers chaos. It wants high entropy. So in order to regain their liquid freedom, the water molecules physically shove the separate oil droplets together into one big clump.
Shoving them together reduces the surface area of the oil.
Exactly. By clumping the oil into one big sphere, the total surface area decreases drastically. That means far fewer water molecules have to be trapped in that rigid ice cage.
And the rest of the water gets to go back to floating freely and being chaotic.
The overall entropy of the entire system goes up.
So it is not that the oil is actively afraid of the water and running away. It is that the water is incredibly cliquey. It violently pushes the oil into a corner just so it can go back to dancing with its friends.
That is a fantastic analogy, yes. It is water's intense desire for chaos, not oil's fear of water, that actually drives the hydrophobic effect.
That completely flips how I picture oil floating on soup.
Mm.
And I think this concept naturally leads us into another big philosophical idea in the field, the concept of emergence.
Yes, emergence. The profound idea that the whole is fundamentally greater than the simple sum of its parts.
Which seems to be the central guiding philosophy of systems chemistry.
It really is. The core debate is this: can we fully predict the complex behavior of a giant system just by deeply knowing the properties of the individual molecules that make it up?
And what is the consensus on that?
The consensus is shifting heavily toward a hard no.
Really? Why is that?
Look at a single solitary water molecule, H2O. If you study that one molecule in a vacuum, absolutely nothing about its chemical makeup suggests the concept of wetness.
Right. A single molecule isn't wet.
Exactly. And it certainly doesn't predict ocean currents or tsunamis or the intricate geometry of a snowflake.
Those are all macro concepts.
Right. Those properties uniquely emerge from the massive chaotic network of billions of interactions. In systems, chemistry researchers are finding that entirely new properties emerge from the network itself that you simply could never predict just by staring at the isolated components.
It sounds a bit like trying to fully understand human consciousness just by poking at one single neuron in a petri dish. You just mathematically cannot do it.
Exactly. The magic is in the network. You need the network to get the mind.
Okay, so we have covered the foundational theory. We have explored the big active debates. Now I want to get to the really visually cool stuff, the gadgets,
The fun stuff.
the frontiers. Based on the sources, what is happening right now that might literally change everything about how we interact with materials.
Well, this is where we get to talk about molecular machines.
Molecular machines.
Yes, and we absolutely have to highlight the 2016 Nobel Prize in Chemistry for this. It was awarded to Jean-Pierre Sauvage-Fraser-Stoddart and Ben Feringa.
So we have completely moved on from static handshakes sitting in a beaker to things that actually physically move on command.
We have. This was a monumental leap forward for science. Sauvage and Stoddart essentially figured out how to mechanically interlock molecules together without welding them.
Mechanically interlock them. How?
They created these things called catenons. which are essentially two completely separate molecular rings that are permanently linked together exactly like a magician's steel
Wait,
rings.
so there is no actual chemical bond holding the two rings together?
None at all. It is purely physical geometry holding them together. They can freely slide and rotate all the way around each other, but because they are closed loops, they can never fully separate.
That is wild. And I also made something called rotaxanes, right?
Yes, rotaxanes. Imagine a single molecular ring that has been threaded onto a long dumbbell-shaped molecular axle.
Okay, so a ring on a stick.
Right. But the ends of the dumbbell are far too big for the ring to slip off, so the ring is permanently trapped on the stick.
So what does it do?
It can slide rapidly back and forth along the axle like a microscopic shuttle.
Okay, sliding rings and interlocking loops are very cool.
Oh,
It
yeah?
definitely proves we can build tiny mechanical parts. But reading about Feringa, he took it to a completely different level, didn't he?
He took it to the ultimate level. Ben Feringa built the world's very first actual molecular motor.
An engine made of a molecule.
Yes. He designed a highly specific molecule that when you hit it with a pulse of ultraviolet light, it physically spins in one specific direction.
I read that directionality is the absolute key factor here.
Mm.
Because if it just spins randomly back and forth, that's just thermal heat, right?
Precisely. Random movement is just Brownian motion. It is practically useless for doing work. But because Feringa's motor is structurally ratcheted to only spin one way, it can actually perform mechanical work.
Like driving forward.
Exactly. His team literally built a functional four-wheel drive nanocar using 4 of these light-driven motors as the wheels.
A nanocar.
Yeah, they placed it on a flat copper surface, zapped it with light, and watched it drive across the surface.
It is so hard to wrap my head around the scale of this. And it reminds me of that famous Richard Feynman lecture from way back in 1984.
Oh, there's plenty of room at the bottom.
Yeah, he asked the scientific community a very simple question. How small can you possibly make a functioning machine?
Feynman was an absolute visionary. He essentially dared chemists to build machines at the nanoscale. And with Feringa's motor, we finally gave him a definitive answer.
Which is yes. We are literally building functional motors that are 1,000 times thinner than a single strand of human hair.
It is a totally new era of engineering.
But what can we actually do with these molecular machines? I mean, driving a tiny invisible car across a piece of copper is a great party trick. But what are the practical real-world applications of this?
Think about the entire field of smart materials. Specifically, we are looking at self-healing materials.
This is the stuff that sounds straight out of a science fiction movie.
It really does. But by using these supramolecular bonds, which again are entirely reversible, we can manufacture plastics and polymers that literally heal their own wounds.
How does that work in practice?
Well, imagine the clear coat paint on your car. If a shopping cart scrapes against it and scratches it, what is happening chemically is that you are violently breaking thousands of these non-covalent molecular Velcro bonds.
Right, you are ripping the Velcro apart.
But because those bonds were never permanently welded in the first place...
It could just reform.
Exactly.
Yeah.
Because they aren't covalent bonds, they have the ability to reform. You might just need to apply a little bit of warm air from a heat gun, or sometimes just let it sit in the sun.
And the heat gives the molecules enough energy to move.
Right. The molecules wiggle around, they naturally find their original chemical partners again, and the physical scratch smoothly closes right up.
The Velcro just sticks itself right back together.
The material autonomously repairs itself back to full strength.
That is incredible. So we are looking at scratch-resistant car coatings. What about bigger structural things like self-repairing oil pipelines?
Absolutely. Pipelines, artificial human skin for prosthetics, even critical components like battery electrolytes.
High for safety?
Huge safety implications. If you have a highly volatile lithium battery inside a flexible smartwatch and that battery casing cracks, a self-healing supramolecular electrolyte could instantly flow in and repair the microscopic crack before it causes a catastrophic fire.
That could save lives.
It really could.
Now, there is another smart material in the source documents that honestly broke my brain a little bit. Porous liquids.
Oh, porous liquids are a wildly fascinating recent development.
It literally means liquids that have empty holes permanently floating inside of them.
I know it sounds like a complete physical oxymoron. Usually, by definition, a liquid fluidly fills all available empty space.
Right. If you poke a hole in a glass of water, the water instantly rushes in to fill the hole. You
Yeah.
can't have a dry hole in water.
Exactly. But brilliant researchers, specifically teams like the Cooper Group, have managed to design what we call cage molecules.
Cage molecule.
Think of them as incredibly rigid, totally hollow molecular spheres.
Okay, like microscopic empty soccer balls.
That is exactly what they look like. And they cleverly engineered the outside surface of these soccer balls to be highly soluble in a specific, bulky liquid solvent.
So the balls float perfectly in the liquid.
Right. But the inside of the ball remains completely, totally empty. And here's the genius part. The actual molecules of the liquid solvent are physically too fat to squeeze through the holes of the soccer ball.
Oh, wow. So the liquid can't get inside to fill the hole.
It can't. So you are left with a flowing liquid that is absolutely packed full of permanent, floating, dry, empty spaces.
Which again sounds cool, but what do we use an empty liquid hole for?
Those specific empty spaces are structurally perfect for rapidly capturing target gases.
Gases like CO2. So this is climate change technology.
It could be an absolute game changer for climate tech. These porous liquids can selectively capture and trap CO2 or methane gas much more efficiently than standard solid filters.
Because it's a liquid, so you can move it.
Exactly. You can pump it, constantly flow it through industrial exhaust pipes, and it literally sucks up the greenhouse gas like a continuous sponge because the microscopic holes are specifically pre-sized to only fit CO2.
That is brilliant engineering. Okay, let's shift gears from saving the environment to saving our actual bodies.
Right.
I want to talk about nanomedicine.
This is an area where host-guest chemistry is actively saving human lives right now. We absolutely have to talk about cyclodextrins.
The donuts.
Molecular donuts, yes. Cyclodextrins are relatively simple, ring-shaped sugar molecules.
Okay, a sugar ring.
And they're unique because the entire outside rim of the donut absolutely loves water. It is very hydrophilic.
So it dissolves completely cleanly in human blood.
Exactly. But the inside of the ring, the actual donut hole itself, is intensely hydrophobic. It absolutely hates water and repels it.
So it creates this tiny, dry, protective pocket floating through the bloodstream.
Like, you got it. And that dry pocket is the absolute perfect hiding spot for a targeted drug molecule that also strongly dislikes water.
Which is a lot of them, right?
A huge percentage of our most potent pharmaceutical drugs are inherently hydrophobic. They simply do not dissolve cleanly in the human body.
So if you just inject them, they just clump up and don't do anything.
Right. They aggregate and cause terrible side effects. But if you carefully trap that stubborn drug molecule deeply inside the hole of a cyclodextrin, the water-loving donut acts as a stealth submarine and seamlessly carries the drug safely all the way through the bloodstream.
And then what happens when it gets where it needs to go?
Then, depending on how the supramolecular system is engineered, the drug is specifically released only when it hits the target cell environment. We are rapidly moving toward a whole new paradigm called theranostics.
Theranostics. So therapy combined directly with diagnostics?
Exactly. Imagine injecting a highly complex supramolecular system into a patient. The system actively swims through the body, hunting specifically for breast cancer cells using molecular recognition.
A lock and key.
Right. When it finally finds the precise cancer keyhole, it binds tightly to the cell. And that specific binding event mechanically triggers a dual reaction.
What kind of reaction?
First, it lights up brightly with fluorescence so the attending surgeon can clearly see the exact margins of the tumor on a monitor.
And the second reaction?
Simultaneously, the physical shape change forces the system to eject its toxic drug payload directly into the cancer cell, destroying it from the inside.
It is literally a microscopic search and destroy mission with its own built-in targeting flashlight.
Precisely. And because it fundamentally relies on that exquisite lock and key selectivity, it completely ignores all the healthy cells in the area.
Which means no more devastating systemic chemotherapy side effects.
That is the ultimate dream of nanomedicine.
Yeah, it really is.
Yeah.
Okay, and briefly before we move to the final section, you also mentioned supramolecular batteries earlier.
Yes, we briefly touched on the self-healing safety aspect, but the technology goes much further than just preventing fires. We are actively looking at the dawn of truly flexible, stretchable electronics.
Like phones you can fold in half, wearable sensors woven into your shirt.
Right. Traditional lithium-ion batteries are extremely rigid blocks, and if you force them to bend, they inevitably crack and violently leak highly hazardous flammable chemicals.
Which is obviously bad.
Very bad. But supramolecular chemists have developed highly advanced dynamic gels that can function as highly efficient battery electrolytes.
So a gel battery.
Right. They are chemically solid enough that they will never leak out like a liquid, But because of the dynamic non-covalent network, they are physically flexible enough to stretch, bend, and twist repeatedly.
And if they do somehow suffer a micro tear from being stretched too far.
Because they are held together by reversible bonds, they just autonomously heal the tear instantly. It completely enables a whole new physical form factor for consumer technology that we haven't even really dreamed up yet.
It really does feel like we're standing right on the precipice of a massive fundamental material revolution.
We truly are.
But with great technological power, always comes the inevitable fallout. Which brings us perfectly to our final section, the implications.
The broader societal, economic, and frankly philosophical fallout of playing with the building blocks of matter.
Exactly. And first up on the docket is perhaps the biggest question in human history, the actual origin of life, abiogenesis.
It is the ultimate mystery, isn't it? How did we get here from dead rocks?
And supramolecular chemistry actually gives us some real tangible clues about how that transition happened, right?
It gives us our best working models. For instance, we absolutely have to talk about homochirality.
Homochirality, I remember this in the notes. That is the biological handedness of molecules, right?
Yes, handedness. Molecules can be built in two mirror image shapes, a left-handed version and a right-handed version.
Like a pair of gloves.
Exactly. Chemically, they are identical, but you cannot comfortably put a left glove on a right hand. Now, in a sterile lab, if you synthesize basic amino acids from scratch, you always end up with a perfect 50-50 mix of left and right-handed molecules.
It's statistically random.
Right. But biological life on Earth exclusively uses only left-handed amino acids to build proteins.
Exclusively left-handed. How did life pick just one side?
That has baffled scientists for decades. But supramolecular chemistry demonstrates that a very, very tiny initial imbalance, maybe just slightly more left-handed molecules randomly created by polarized radiation from a distant passing star.
Okay, so a tiny cosmic nudge.
Right. That tiny initial imbalance can massively amplify itself through a process called autocatalysis.
Autocatalysis, what does that look like?
Once you have a slightly higher physical concentration of the left-handed version, they naturally begin to form massive supramolecular assemblies. And those specific assemblies physically act as catalysts to rapidly speed up the production of even more left-handed versions.
While actively ignoring or suppressing the right-handed ones.
Exactly. It is a runaway winner-takes-all chemical mechanism. It clearly shows us the mechanical pathway of how early life could naturally select one specific chemical path out of chaos.
And that leads directly to the research on protocells.
Proving it in the lab, we are inching incredibly close to creating a form of basic life in a test tube.
It really feels like we are crossing a major line there.
Researchers are actively creating these artificial vesicles, which are essentially just very complex chemical soap bubbles that can autonomously grow, continuously divide themselves, and actively maintain an internal chemical gradient that is different from their outside environment.
So if we actually succeed, if a team tomorrow genuinely creates a fully self-replicating metabolic chemical system in a lab beaker, is it legally and ethically alive?
That is the massive looming ethical question we are not ready for. Do we desperately need new bioethical guidelines for what they're calling wet artificial life?
Because it's not a computer program, it's physical chemistry.
Right. If I intentionally pour that successful beaker of protocells down the lab sink with some bleach, am I technically killing a living species?
Wow.
If a droplet accidentally escapes the lab on someone's shoe, can it survive and autonomously evolve in the city sewer system? These are deeply terrifying questions that we absolutely need to answer long before we actually succeed, not panic and try to answer them after the fact.
That is a deeply unsettling thought to just sit with. Let's pivot slightly to something a bit more immediately practical. Sustainability.
A much more solvable problem, yeah.
We mentioned carbon capture porous liquids earlier, but the sources also brought up the massive ongoing issue of forever chemicals, the PFAS.
PFAS are incredibly nasty environmental pollutants. They are heavily used in non-stick Teflon pans, specialized firefighting foam waterproof jackets.
And they are called forever chemicals because they literally never chemically break down in nature.
They just accumulate permanently in the groundwater and eventually inside our own bodies. But supramolecular chemists are fighting back. They are designing highly specific hosts, like heavily modified versions of our donut friend, the cyclodextrin, or specialized porous polymers that are engineered to bind exclusively to PFAS molecules.
So they act like a molecular sponge just for the poison.
Exactly. We can deploy this specialized molecular recognition to actively hunt down and catch the trace pollutants that are physically too small or too chemically stubborn for standard municipal water filters to catch.
It acts like a highly specific targeted chemical trap.
Yes, it is environmental remediation at the molecular level.
And what about the actual manufacturing side of things? How does this impact green chemistry in the factories?
There is a massive global push right now for what is called solvent-free synthesis.
Because traditional chemistry uses a lot of toxic liquid solvents.
Right. Oceans of it. Often a standard chemical reaction requires vast amounts of highly toxic volatile solvents that ultimately create thousands of tons of hazardous chemical waste that has to be burned or buried.
Which defeats the purpose of being green.
Right. But supramolecular chemists are increasingly championing a technique called mechanochemistry.
Mechanochemistry, which is literally just grinding things together.
It sounds primitive, but literally, yes. They put two dry chemical powders together into an industrial ball mill and aggressively grind them together.
And that actually works.
It works beautifully. The raw mechanical force of the grinding physically drives the supramolecular molecules close enough together to shake hands and form the assemblies.
So there is absolutely zero toxic liquid solvent used and zero chemical waste generated.
It is infinitely cleaner and safer.
And what about the end of the product's life? Biodegradability.
This might be the single biggest commercial advantage of switching to supramolecular plastics. Because the non-covalent bonds are inherently reversible, we can intelligently design materials that are incredibly tough and robust while you are using them.
But then when you throw them away,
We can trigger them with a specific mild chemical or a specific wavelength of light to completely unzip themselves right back down into their original harmless microscopic monomers at the end of their useful life.
so it is true closed-loop recycling, not just melting down a dirty plastic bottle into a slightly lower quality park bench until it eventually becomes useless microplastics.
Exactly. It is literally turning the fully glued Lego castle smoothly back into a pile of pristine individual Lego bricks ready to be built into something entirely new.
That sounds like exactly what the world needs right now. But obviously we have to address the harsh commercial and economic reality of all this.
The eternal bottleneck. Scalability.
Right. Because it is one thing to do this in a multi-million-dollar lab and another to sell it at a hardware store.
Exactly. It is relatively easy for a team of PhDs to carefully synthesize 1 single milligram of a beautiful molecular motor in a pristine research lab.
It might take them 10 highly complex steps and cost $10,000 to make that one microscopic speck.
Right. It is exponentially harder and massively more expensive to manufacture a full industrial ton of that exact same smart material to actually coat a real suspension bridge in the physical world.
So the core economic question becomes, is the smart material actually worth the massive extra cost up front?
That is the ultimate commercial trade-off. Is a construction company willing to pay literally 10 times more per gallon for a high-tech supramolecular paint if it mathematically promises to heal its own microfractures and functionally last 20 times longer than standard dumb paint?
The long-term math says, yes, it is worth it. But that initial upfront sticker shock is a huge barrier for a budget.
It is a massive barrier. But we are slowly moving from a deeply entrenched top-down manufacturing economy where we brutally carve things out of massive blocks of steel and wood and generate a ton of waste to a completely revolutionary bottom-up economy.
Growing things atom by exact atom.
It completely rewrites the basic economics of global manufacturing. Biology already exclusively builds bottom-up.
Right? A giant oak tree doesn't cost $1 million to build.
No, it seamlessly builds its own massive complex structure, completely autonomously, using nothing but ambient solar energy water and the carbon in the thin air.
If we can truly master supramolecular manufacturing, we can potentially grow incredibly complex industrial products with almost zero energy input and zero waste.
It would fundamentally alter human society.
Well, finally, as we sort of wrap up this extensive exploration, I want to zoom out and talk about the fundamental shift in philosophy here, the shift towards systems thinking.
This is honestly the biggest lesson I personally take home from studying this field. We are finally learning as a scientific community that the connection between the pieces is actually just as vital as the piece itself.
In chemistry, and honestly in life.
Precisely. You fundamentally cannot understand how a human cell works merely by writing down a long list of its internal proteins.
Just like you cannot truly understand a complex human society merely by reading a census list of its individual citizens.
Exactly. You absolutely have to deeply understand the invisible interactions between them. Supramolecular chemistry vividly teaches us that truly complex emergent behaviors, things like biological life, conscious thought, physical resilience, all uniquely emerge from the vast chaotic network of incredibly weak, flexible connections.
The invisible handshake is actually more important than the physical hand.
That is a genuinely beautiful way to put it. Yes, the future of science is entirely about adaptive materials,
Materials that actually learn from their changing environment.
materials that physically evolve over time. We are decisively moving away from a static, boring world made of dead, unyielding matter toward a highly dynamic world of deeply responsive, almost living physical systems.
So what does this actually mean for all of us going forward? It means we're looking straight at a future where the rigid line between biology and human technology completely blurs away.
It will become entirely indistinguishable.
A future where our shattered phone screens quietly heal themselves in our pockets overnight, where our daily medicine actively hunts down a specific disease like a microscopic predator, and where our giant industrial factories don't assemble products on a noisy conveyor belt, but actually grow them silently like a garden.
And every single bit of that miraculous future starts with deeply understanding that one delicate, reversible little handshake between two invisible molecules.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.